Good morning, everyone. I hope you had a good night yesterday and you enjoyed the first day and ready for an amazing day that we have scheduled for today, starting with such a wonderful, wonderful keynote speaker. It's really my honor to stand here to introduce Dr. Youssef Hashash. For the people who knows Dr. Hashash, he's a professor who holds a bachelor degree in 1987 in civil and master's in 1988 and PhD in 1992 from MIT. He began his career with the PBMK team in Dallas on the superconducting Super Collider project. In 1994, he joined Parsons in San Francisco to work on many of underground construction projects in US and Canada, including the Boston Central Artery Tunnel project. Professor Hashash joined the faculty in the Department of Civil and Environmental Engineering at the University of Illinois in Urbana-Champaign in 1998. He teaches courses in geotechnical engineering, numerical modeling and geomechanics, geotechnical earth engineering, tunneling in soil and rock, and excavation and support system. His research focus includes deep excavation and tunneling in urban areas, earthquake engineering, continuum and discrete element modeling of soil structure interaction, as well as resiliency and sustainability of the built infrastructures. He also works in geotechnical engineering application of deep learning, artificial intelligence, visualization, augmented reality, imaging, and drone technologies. He is geotechnical co-leader of the NIST, National Institute of Standard and Technology, led investigation into a Champlain Tower South collapse in Surfside, Florida. Professor Hashash is a fellow of the American Society of Civil Engineers, a past president of the Geo Institute of American Society of Civil Engineers, and has received a number of teaching, university and professional awards, including the Presidential Early Career Award for Scientists and Engineers and the ASC 2014 Peck Medal. He was elected to the U.S. National Academy of Engineering in 2022. Before bringing Professor Hashash to the stage, I learned from yesterday from Reginald bringing fun fact. So let's do a fun fact about Dr. Hashash. I will tell you what I'm after. I asked him yesterday about some of interesting things that, here we go. Have you heard about this word? The one who knows what is this, there is a big gift certificate at the information. $50 of Amazon. I'm serious. I Googled it. I started to learn a lot yesterday. Any ideas? Okay. It collects butterflies. So basically, I think as a child in Lebanon with these beautiful mountains, I don't know if you've been in the Middle East, in Lebanon, they have beautiful mountains there with a lot of butterflies. He collects a series of butterflies. So I'm sure he will be the expert. So anybody interested in butterfly, talk to Dr. Hashash at the end. It's an honor to welcome Dr. Hashash to the stage.
Thank you, Dr. Yaqub, and thank you very much, everyone, for being here today. I really appreciate the invitation to speak before you today, and I hope to take you on an interesting journey, so bear with me. Since we were talking about mining, I actually worked on a mine in Canada. So those of you who may know, it's called the Cigar Lake Mine in Saskatchewan. So I worked on that many, many years ago, did numerical modeling, and that was the deepest I've ever been underground, around 500 meters. So it was quite the adventure, actually just getting there. So today I'm going to talk to you about the discipline that is beloved to all of us, geotechnical engineering, and it does, covers both rock and soil. You may see me talking maybe more about soil, but some of the concepts and ideas are equally applicable. in this current age, we hear a lot about machine learning, AI. Do we have a role there to play? And how is all that that's going on going to affect us or not? So first, I want to acknowledge my colleague, Professor Jamshid Ghabousi, who really I consider him my mentor in that area, and also many of my students who, as a faculty member, you are what you are because of your students. So I'll give you, this is sort of the outline of the talk. I'll talk about the role of data in geotechnical engineering. I'm not going to spend too much time because my good friend, Dr. Rathji, spoke very nicely about it yesterday. But it's a good segue to talk about the rest of the topics. What is artificial intelligence? Some introductory comments, some background to give us some perspective on that. I'll give you some selected applications of AI in geotech engineering, sort of a straightforward application. And then I'm going to talk about how we extract underlying behavior. That's where the true learning comes into play. Then I'm going to talk about generative AI, something that is making the buzz nowadays. And let's see how that might impact us. And then into the future. Now, I have to say, if I really knew what the future is, I'd be a very rich person. But I might as well speculate. So data in geotechnical engineering. We have to always keep in mind that what we're working with is the ground. It's all about geology, engineering geology, as we heard earlier in this conference today, on Monday. And we are dealing with material that is highly variable, has nonlinear behavior, and it's anisotropic, and a lot of non-uniformity there. So we are always trying to collect data information about this material, about our site, and the scales vary depending on the problem you are working with and the infrastructure. There's been, from the beginning of modern day geotechnical engineering, going back to, say, the days of Carl Terzaghi, brought in concepts, ideas from different disciplines. If you think about it, it's the buoyancy, flipped it, became an effective stress, and then advanced, bringing in variety of theories to try to decipher this material, try to give us an idea of how to deal with it. Now, Carl Terzaghi recognized early on the importance of the field and laboratory, but also the importance of theory. And his book, Theoretical Soil Mechanics, is a testament to the importance of that. But he recognized the importance of all of this. And the question would be, can we extract something more fundamental in terms of behavior? That's the same thing that Carl Terzaghi has to deal with at the time with our modern laboratory tests and data processing techniques. We're still doing laboratory testing, field testing, data collection. The question is, do we keep on doing it the same way, or should we be doing it differently? The observational method has been very fundamental. It's a cornerstone of geotechnical engineering. And kind of the terms were coined during the work on the Chicago subway, where a young engineer by the name of Ralph Peck was the deputy of Carl Terzaghi to go and watch over construction. Professor Peck carried these concepts further and developed them and coined the term of the observational method. And the idea is you develop an initial design, but then you have to adapt during construction as the true nature of the ground is revealed and the true nature of the construction, means and methods, happen. Our data collection tools have evolved. We had the remote sensing from the very beginning, sort of early 1900s. But nowadays, we're dealing with things such as INSAR and the Internet of Things in terms of monitoring. We are able to collect a lot of data. Our interpretation tools range from simple graphical interpretations, which are, by the way, extremely important for us, to artificial neural networks, these really interesting black boxes that do things that we like to think that actually are relevant and important for us. In geotechnical engineering, we've been working with machine learning since the very beginning. This is the OG, the original type of machine learning, whereby you're looking at a correlation between an allowable soil pressure and with a footing vis-a-vis different types of soils, for example. Other types of correlations, you can think of them as what we call now shallow machine learning. These are the correlations that we use extensively in geotechnical engineering, and that's really something that it's important now with the new tools to think about it in the right context as well. Of course, when we started the modern adventure of geotechnical engineering, we were suffering from the lack of data. We are facing the opposite problem nowadays, which is a lot of data, maybe too much data. Or maybe it is that we do not have the appropriate tools to manage that data and tease out, extract knowledge, information from that data that would be helpful for us. So that is something that we want to explore. So let's talk a bit about artificial intelligence. Those of us who have been around the block a lot have seen booms and busts in that technology. And it seems we're at the cusp of something different nowadays. If you know about Alan Turing, he solved the Enigma, was a major role in defeating the Germans during World War II. Actually wrote about it in a journal called Psychology and Philosophy, which is interesting. Computing machinery and intelligence is what we want is a machine that can learn from experience. So the idea of artificial intelligence is not new. It's just that people had a vision, and it took a while to realize that vision. So the AI we know, if you go to the iRobot, of course, the Terminator and series of Terminators, and it was a big deal when I was at MIT. They would show it for the students, and they would have a counter of the, shall we say, the number of people that get terminated in there. And then, of course, Star Wars, which I love, and, of course, the rise of the drones. Well, we are living, actually, if you look at it, in the age of drones, and we're seeing it in many different ways. And, of course, if you've been using, any number of those assistants, and nowadays it's ChatGPT. And these are with us. And I think if you recall yesterday, I think Dr. Rashi's assistant kind of kicked in for a little bit, unbeknownst, unintended, but it's listening. Okay. So when we talk about AI, we are talking about many, many different things. I'm going to cover very few of them, but I want you to recognize that the field is much larger than just one thing or the other. And so this is from Rome 2021. So artificial intelligence, the science and engineering of making intelligent machines. And really the term intelligence, I think, sometimes can be an exaggeration and sometimes can be used as a way to think about a machine that can do certain tasks in a way that we don't have, it saves us time. There's a planning type of tools for to build control algorithms. That's part of AI. Natural language processing, and that's really what we really want, is the ability to speak to the machine, and the machine executes or does things for us. And then there is the machine learning. That's another category, to learn without being explicitly programmed. And then you have the deep learning, which is really, we use often types of or classes of artificial neural networks or some other systems. AI in civil engineering, people have been exploring its potential for quite a while. going back to 1966 on artificial intelligence and design of structures. This is where there are indications that the major development in the next few years, well, it took a little bit longer than that, will be in this direction. That is possible to have an adaptive type of structural design system. In 1986, we've heard a lot, if you remember at the time, people talk about expert system or knowledge-based system. It's still talking about the same thing. And that there is survey results indicated a long-term commitment to research and development of expert systems. And then in 1991, my colleague, Professor Jamshid Ghabousi, and I had really a privilege of many conversations with him. He told me he used to go to conferences about the brain when he kind of started looking into these, introduced the concept of using artificial neural networks to represent material behavior in civil engineering. It's going back to 1991, and it's a pioneering work, actually. It's a landmark work. So let's show you some selected applications in geotechnical engineering. I'll talk to you about first tunneling-induced ground response, seismic site response analysis. So let's start with the tunneling-induced ground response. I'll talk about 3 topics: operation optimization, ground condition estimation, and then tunneling-induced settlement estimates. So modern tunnel boring machines are amazing technological innovations. If you haven't had the chance to be familiar with them, I encourage you to do that. They're highly automated, very capable, and they're in fact allowing us to tunnel through ground that would have been difficult otherwise, or not using non-mechanized tunneling machine technology. They have a lot of sensors throughout. That's how they do a variety of controls. The number of sensors is a lot, and I'll give you a sense of the data in a minute. But there's all this data. If you think about the tunnel boring machine, it is one big borehole or CPT or a probe that you're taking through the ground. And it's reacting to the ground. So can I use it to tell what the ground is or how the ground will behave? Well, can I take that information that I'm collecting, do that? So the first thing, so we have TBM operations. You're trying to steer it, make sure the tunnel goes in the right direction. And then trying to figure out how to adapt to varying ground conditions, because no exploration program is perfect. And then how we can do some type of estimate of ground movements. That's a really big deal in urban areas, whereby you are trying to minimize ground deformations. So I'll talk to you about AI applications in these 3. So let's talk about the operation optimization. What it is you're trying to make sure that TBM remains on track. And if you've ever been down in a TBM and looked at the controls, there's that kind of cross, and you're trying to make sure the dot is matching it. And you can manually adjust the various controllers or to align it, or you can actually use an AI type of model. So this is from a paper in 2019 at the ITA tunneling conference. And you're looking at, on the horizontal axis is the timeline, on the vertical axis is the deviation from the target alignment. And the yellow lines represent acceptable bounds. If you go beyond it, you're really getting into a territory that you do not want. And this is a manual control, and you can see how there's a lot of oscillation. And this is all controlled by an operator. But now if you use a planning AI type of algorithm, you can see it very rapidly converges to the exact location. It's taking all that feedback from the various sensors, various actuators, and now it's able to steer it at a level of precision that is unprecedented. And that's because we took the human out of the loop and letting an AI planning algorithm do that for us. So now let's talk about another one application from these tunnel boring machines, and which is ground condition estimation. So we have a collaborative work with NSF and Los Angeles Metro, where I think some of you know there are several lines that are being built and more that's to be built. And the idea is to see, can we get all of their extensive data, monitoring data, and try to make sense out of it. So we picked several lines. We're collaborating with them, and this is an ongoing effort. And fortunately for us, part of an extensive collaborative effort, we are able to access all the data that they can provide us. And so we're looking at the Crenshaw line here, and there is a data along this line. It's just 1 mile long. We have about 3 million ground movement data points and 1 billion tunnel boring machine sensor data, okay? We cannot, as people, human, deal with this data. We then, therefore, selectively pare it down to make sense out of it. But therefore, we're actually losing a lot of information. Can we use all that information? So one thing we try to do is to have all that TBM input to try to estimate ground condition. And differing site conditions is always a big deal in tunneling. So we went through a lengthy exercise, and I can kind of elaborate on it later on if you want in the Q&A of how we selected those. But we selected this data, and we used an artificial neural network which has an input layer, an output layer, and 2 hidden layers for that. The exact architecture of the neural network, by the way, does not matter as much. It has a little bit of play, but this is not the purpose of the conversation here of how to select it. And the idea was, okay, if I use that input, and then can I have soil labels so that I can look at the ground? For training data, we used the site exploration data. They had a number of boreholes along the alignment, and we assumed that that the soil label applies to within a diameter of about 25 feet around each borehole. And so this is one borehole at station 42 plus 500, and this is the ground condition at the tunnel horizon, by the way. And then we use that to develop training data to train our data. And this is, for example, one kind of measure we had of the advanced force. And we use the data and within that 25 feet to train our neural network. So at the locations where we have boreholes, that's when we extracted the data. But then we also split it. Part of it is for training, and part of it is for prediction. And we ended up with having about 5,000 TBM locations can be labeled from one borehole, because remember, the resolution of the TBM is very high. In fact, for a reference, the TBM recording frequency is 0.01 foot. CPT sampling frequency is 0.1 to 0.3 foot. So you have a higher sampling frequency from a TBM compared to a CPT. Think about it that way, okay? So we need to start thinking about these considerations in how we now use all the tools available to us in ground characterization and addressing our engineering problems. So we had about 65,000 TBM locations with data to label from 21 boreholes. And then we ended up, the remaining locations would be 424,000 locations with and without labels. So for model training, and then we generate continuous profile for where we don't know the information, and let's see how that works. So we split the data 70-30, 70 for training. That's where we know the information from boreholes. And we had the confusion matrix. We heard about the confusion matrix yesterday, and it showed us actually pretty high. So look at the diagonal part, the value close. 1 is like perfect prediction, but as you can see, the numbers are very, very high for the testing data, for the training data, and for the whole data set. So we're doing very, very well, correlating the data with the ground condition. And so then we said, so we had about 88% accuracy. Good enough, in my opinion. So then what we did is we said, okay, so if you're an engineer, you're going to develop a soil profile, right? So that's the soil profile you do, which is an interpretation, an interpolation between the boreholes, right? That's what we do. Sometimes you put it in the baseline report on which you base the differing site conditions on. And then what we said, okay, so let's use now our artificial neural network to see what it would tell us about the ground conditions between the boreholes. And so, and this is, we have our predictions, our estimates. I can't call it prediction. And you can see, and we're using the same color scheme that you would have along the tunnel alignment and also through the southbound and northbound tunnels. And if you look at the shading, we have pink, yellow, and blue. It actually corresponds very well to what we would have interpreted. And in some places, it shows us things that are different. And maybe they are indeed different than our interpretation. I'm not saying our geotechnical interpretation, the profile, is necessarily correct. It's our best estimate. But now I have TBM data that I'm using to interpret it that way, and I consider it potentially equally valid as to what kind of ground conditions we've encountered. So it does a pretty good job, and it has a role to play. And it's not only here, of course, you say, well, you already had it, completed the project. That's fine, but think about projects where you're doing things on the fly. We can do that. Training these neural networks is not time-consuming. It's pretty easy to, fairly quick. So now let's talk about another application here, and that would be tunneling-induced settlement estimates. The same, similar set of input, and then we looked at the output for that. And so this is the alignment stationing along the alignment. Vertical axis represent the settlements, and the blue points are the measured settlements. And then we did all the training the same way, and you can see the estimates of settlements track very, very well with the measured settlements. So we are able to do that. So that's useful in areas where you have potentially missing data or you have some concerns, because you can now use the TBM parameters to have an estimate of what kind of ground deformations you get, and that will help you in imposing controls on the TBM. And it could even be potentially used by owners to make sure that the contractor is indeed doing a proper phase control, proper shield control, pressure controls to make sure that the ground deformations are limited. We're extending those. Actually, we have already extended them to other lines on the LA Metro, and they actually work well. And that's the exciting thing about it. Let me shift now to another application. I'm trying to give you a sense of where we can apply it and how successful we are. Another one is site response analysis. This is something that Professor Raschi and myself have been working on for years, actually, with other colleagues as well. What's the problem? Is that if you have a ground shaking, the ground motion at a rock site will be different at the soil, because the soil itself does something to the ground motion. It filters usually high frequencies, and it amplifies low frequency long periods. It causes site amplification. And the definition, we are going to talk about the definition of an amplification factor, which is a measure of the ratio of an intensity measure at the surface over an intensity measure at the rock. It could be peak ground acceleration, for example. And we decompose it to two components, a linear and a nonlinear component. So a classic model would look something like this. The amplification ratio, it's a natural logarithm of it, would be a function of VS30, which is the time average shear wave velocity over the top 30 meters, plus, say, for example, effect of natural period, plus a nonlinear component. Now, we wondered if can a neural network do something similar, whereby I'd have the exact same input, and then I would have some similar output. So there what we did, this was a study as part of NGA East Next Generation Attenuation in the Eastern North America, where we do not have lots of data. So we did a lot of simulations. We did a large-scale series of simulations. It's actually the largest ever been done, whereby we encompassed varying ground conditions, a lot of different soil properties, depths, rock condition, and we performed linear analyses, equivalent linear analyses, and nonlinear analyses. This is using software called Deep Soil. Some of you may be familiar with it. We ended up with about 3.6 million simulations. You can't do simple regressions with these. Well, we tried to get an estimate of these with these models. And we developed some amplification functions, which, by the way, some of them are already being used by the US Geologic Survey in their hazard maps. This is one way of presenting the data. Looking at the horizontal axis is the VS30, vertical axis, the linear amplification, and this is showing you the simulations. This is showing you the bin mean of the data. And then we're looking at a conventional functional form for the amplification function. This is a model called L5, which has both VS30 and natural period. And you see how it covers the data. And then we have an artificial neural network. We use the exact same input with the data. And what's nice, artificial neural networks are data hungry, and we had a lot of data to use them. So, and then what was interesting, so the artificial neural networks were able to capture this behavior. But what was interesting is when we looked at the root mean square error, the same data, one was used for a conventional regression, one was for an artificial neural network. We ended up with a 21% reduction in root mean square error of linear site amplification on a log scale, by the way. Just keep that in mind. It's a log scale, which means it's a huge reduction in the error. Same data, same input. So if I give you something, I would hope that you would jump to the one that doesn't give you as much error. And in this case, it's an artificial neural network. It was able to capture the whole behavior. Everything I've shown you thus far is what I would call as sort of a rather simple, though I mean the word simple is maybe too much, application of, say, artificial neural networks. Now, is there a way to actually extract underlying behavior, truly discover behavior? Something that is really difficult for us as geotechnical engineers. So I'm going to introduce to you the self-learning concept. And again, I acknowledge Professor Jamshid Ghabouzi, who took me under his wing when I was a very young faculty member. And we spent lots of time talking about this. I'm going to give you an applications to excavations, laboratory testing, and then how we can use that to predict real problems. So let's go back a bit to feedback control theory. Feedback control theory, I think most of us may be familiar with cruise control. You set the speed, and usually if you're doing it manually, you have to do it yourself. You put your foot on accelerator or the brake, and you adjust your speed. I know we're not very good at maintaining the speed that way, right? And so there is an input, and then there is an output. Now, of course, people have introduced the automation of that, which is a speed cruise control, and it actually does a very good job, but it's dangerous, right? Because if there's a car in front of you, it could hit it, and hence adaptive cruise control. The relatively newer cars have that. I love it. It's great for long-distance driving. I don't have to worry about it. The car itself accelerates, decelerates depending on the car in front of you, and reaches a maximum of the speed you set. So that's kind of control theory is really, in essence, what the observational method is. And so now let's kind of look at another way of looking at the observational method. You have your engineering design objectives. You develop your site investigation, modeling. You have your engineering design. You go for construction. You collect the data. And then you try to see, is it matching your estimated behavior? Not, you make adjustment and you continue. Can we automate pieces of that or all of it? And that's where it becomes a problem. So I'm going to talk, we have the large data sets. I'm not going to spend much time on that. Talk about an AI-enabled system update. In order to do the update, it is actually an inverse problem, right? And there are the regular problems. You have an input, system model, output, right? You are pressing the accelerator, and then the car speeds up somewhere. And then when you see the speed, and then you readjust say the pressure, or automatically the car controls. There's another type of inverse problems. You know the input, you know the output, you just don't know the system model. And then there is one whereby you know the system model, the output, and not the input. The ones we're concerning ourselves with for the observational method, which is a form of a control loop, is actually this type 1 inverse analysis problem. So now let's talk about a self-learning concept. So in the field, and I'm going to talk about excavations. Those of you who know about my background. I did a lot of excavations from starting with my PhD work, whereby you have some construction sequence going on, so you know that, hopefully. You kept a good record. And then you have instrumentation, you've measured the response. Now, we always talk about the field is our lab, right? I mean, that's what we say in geotechnical engineering. And the behavior, we're measuring a behavior that is a result of a fairly complex interactions of our soils. So can we extract that underlying soil behavior? And of course, I'm here to say, yes, we can. And let's explain to you why, how. So the way the self-learning concept works is the following. So I have two things. This also comes from background in finite element modeling. You have equilibrium and you have compatibility. Equilibrium is the equilibrium of forces. Compatibility is displacements and strains, okay? So the first analysis we do in this, we do a conventional analysis whereby we're removing our soil layers, and this would be an equilibrium type of analysis. Of course, our finite element analysis will give us both strains and stresses, but since the force and stress conditions are most correct, we're going to say that the stress field that I'm going to compute in this analysis is correct, or closest to the correct value of stresses throughout the system. Then I'm going to run a second analysis. And in the second analysis, I'm going to impose my deformations. Okay? I'm not going to impose the construction sequence. I'm going to impose the deformations with an appropriate boundary conditions. And I'm going to say, because of compatibility constraints, the strains I'm going to get out of that are going to be probably reasonable. So from one analysis, I'm going to get stresses. From another analysis, I'm going to get strains. Stress, strain, soil behavior, right? So now, instead of using a conventional material model, I'm going to use an artificial neural network material model. Initially, I'll train it to represent linear elastic behavior over a small range. But when I get those stresses and strains, I'm going to retrain my artificial neural network, and I'll forget the data on linear elastic. I repeat that for a given stage of construction, and then I repeat it for all stages of construction until the stress-controlled and the displacement-controlled analyses give me about the same answer. That's the conversions. And then I will make a claim that the resulting material model closely represents the behavior that is relevant for this problem. You probably notice I'm using a lot of cautionary or qualifying words there. Now, when I mentioned inverse problem, you're probably thinking uniqueness. Well, we can talk about that in a Q&A answer. I should just let you know, all the applications we've done with this problem, we've never run into a uniqueness problem or non-uniqueness. So, and then we can claim that we can use it in a forward problem. So I'm going to show you how we've applied it. Now, again, this has been enabled by our ability to collect massive amounts of data. We can actually scan all the details of our construction sequence so that you need to be faithful to the construction sequence in the field. It doesn't matter what's on the design drawings if you not go out to the field. So I actually had in many places to go down to our resident engineers to actually take the sketches from their drawers, which they were about to throw away, so I can have a correct construction sequence. And then the data. And we applied it to one is the Stata Center, and thanks to Professor Whittle, my former PhD advisor, who got access to all of that data. And we started, we had some sections there, so we can actually do some self-learning or perform some self-learning simulations. This is the data of the measurements. And then what we did is we initialized the material model, the first analysis, to represent linear elastic behavior over its defined strain range. And that was the initial estimate. So sort of it's an elastic initialization. Then what we did is we started learning. This is from stage 3, and then from all stages. So you may say, okay, so what? You've learned what was there. Remember, our objective is not just learning the prediction of the displacements. We are interested in extracting the underlying soil behavior. I'm starting from a linear elastic behavior, and I ended up with some type of interesting neural network that can give me this behavior, which actually includes things such as small strain nonlinearity and other factors. So what we did is we wanted to see, okay, how does the behavior computed by the artificial neural network relative to the measured in the lab? And this is some data that existed way before we had this information. The dashed line represents the initialization of the neural network. The symbols represent laboratory data. And the black line represents what the artificial neural network would give us for this. Now, you can look at the glass as half full or half empty. Half full meaning you didn't match the lab data. Half full would be, wow, we've actually were able to evolve the behavior to get close to that. What we learned is that it's important to you will get close to the actually laboratory measured behavior, but you don't have to actually exactly match it. Remember, when we do things in the lab, we have our other limitations, right? It's a sample that we selectively picked under certain conditions, and then you have the whole field conditions, the in situ conditions that would vary. We've tested that on many different applications, different excavations, and it's been fascinating to see how we were able to represent the small strain behavior. So that kind of got us thinking about, well, how about laboratory testing? Should we still do it the same way as we've done it before? Well, usually we've been striving to make sure that the triaxial test, you impose stress conditions as uniform as possible so that you actually represent a single element. But that's a problem, because then I have to do so many different tests to capture conditions under multiple stress paths, which is what you actually need in your finite element analysis. You need to represent behavior under very complex paths. So we said, okay, let's now make the triaxial test deliberately non-uniform by putting in lateral constraints. We built a device, we did photogrammetry there to collect all that data, and then we started training it. And so this is an interesting figure. On the vertical axis, it's a b-value, tells you something about the intermediate principal stress relative to the major and minor principal stresses, and the horizontal axis represents principal stress direction. The triaxial test, conventional uniform triaxial test, is a single point at the bottom left. It's a single point, okay? Triaxial extension is a single point. From this single test, now we plotted our stress path and the data points, and you see how much of the space it covers. And that could only be extracted through self-learning simulations because we did an inversion essentially there. We did these parallel analysis, stress controls, displacement control. So we applied that concept. We said, okay, if that works, remember the DSS, direct simple shear. We don't like it because we don't know the state of stress very well. But actually, it's a fantastic boundary value problem. And so we used it, we treated it as a boundary value problem and applied self-learning simulations to it. And we extracted behavior, and it covers a pretty nice part of the stress space. And this is the DSS on Boston blue clay, for which I had my excavation problem. So I said, okay, so now if I take my DSS test, the neural network that's trained from the self-learning simulations for the DSS test, and try to predict the excavation, do I get anything reasonable? Single test. Keep that in mind. One laboratory test. Well, guess what? We use the same problem. So first I'm going to show you this is the measured data is the black. The blue is the self-learning simulations from the actual excavation. And then the last one is from the DSS test, whereby I did not use any data from the excavation and look at the predictions. This is, of course, still qualifies as a Class C prediction, but we did not use any of the data from the actual excavation to do this prediction. Now again, glass half full or half empty. If this was actually a prediction in an engineering design, people will be having a party, okay? Because it's that good. Yes, there are places where it wasn't measured, didn't match very well, but that's okay. So now let me go to the last part of my presentation today. And that's generative AI. It's the buzz nowadays. I'm going to talk to you a little bit about what is it, and then we'll go about a few things. Can it write a report for us? Can it give us a technical advice? Can it write a code? Data mining I'm going to skip. do desktop studies and some integration of the tools. So generative AI is that AI that creates new content, such as text, images, or sounds. ChatGPT-3 is one. I'm sure you've heard a lot about it, and you might have played with it. Bard is the competitor from Google, and it's a race now to work on that. So DALL-E for image creation, if you're not familiar with it, is from the same OpenAI project. And there is a sound that can generate music, and actually people have generated music from it. And there are some other ones as well. So you can ask ChatGPT to explain itself, and it says, well, it tries to generate human-like responses and assist in technical support. What data is ChatGPT trained from? A lot, okay? And I think it continues. Every time it evolves, it has more data, more information, it builds on it. So we said, okay, well, can it be useful for geotechnical engineering? So the first thing we asked it is the following. Gave it a prompt. There's a sandy silt embankment with standard penetration testing, so and so blows per foot. Could you write an example geotechnical report? And ChatGPT gave us the following, okay? Let me put it this way. It did better than a first-year master's student. I'd like to say probably better than a first-year engineer that you would hire. Not to leave Bard behind, it did something pretty similar. Let me put it this way. It is shocking how good it is, okay? Given that it's still a baby, okay? Now, technical advice. So we had a mid-rise building in Seattle with some CPT tip resistance, with an acceleration 0.5 G, sandy layer between 10 and 15 feet, and give it a thickness of 5 feet. Will there be liquefaction? The groundwater is 5 feet below the surface, and the fines content is 2%. This is literally the prompt that was given to ChatGPT. And this is what it did. It made a mistake. It flipped the stresses for calculation of the CSR. Remember, it's still a baby, okay? But it kind of got a pretty good idea of about what to do there. Bard, this is Google's, was a little bit more cautious, but it said that you're likely to have liquefaction, okay? So it ingested enough information from the world to actually make something that I'd have to say is sensible. Definitely better than some of my students in starting with the earthquake engineering class. Okay, so can it write a code? So we said, can you do a one-dimensional rod wave propagation? And it did that. It provided that. So now let's take a look a little bit into the future. How can machine learning be applied in geotechnical engineering? We literally asked that to ChatGPT, and it said predictive modeling, material characterization, geotechnical investigation, risk assessment, construction management, and it says, it has the potential to revolutionize geotechnical engineering. I have to agree. And it says, and then we asked it, I'm a civil engineer, can ChatGPT please take over my job? Well, let's look at what ChatGPT said. Said, well, I'm not able to replace a civil engineer. Additionally, a human engineer has the ability to think critically, make decisions, and solve problems. Please consider me as a tool. So it talked about a human engineer versus now the non-human engineer. Bard was not as shy. And it says, I hope that one day I will be able to take over your job, but for now, I'm still learning and growing. Watch out. I appreciate your patience and understanding while you retrain for some other job, I guess. So what is a geotech to do? Let's go back to our modern roots. Carl Terzaghi says, I recognize weak points in traditional procedures and try to make them less weak. We need to maintain our human sense, but also identify room for improvement in our practice. And this is where these new tools are. But they are incredibly powerful. Just imagine a generative AI that's been trained on all geotechnical literature in all languages, and not only geotech literature, all structural literature, all civil engineering literature. it is likely to be a better engineer, at least than many we know, because it's able to make connections. So that leads me to my conclusions, and I'm a little bit over my time, so thank you for bearing with me. The tools of geotechnical engineering have changed drastically over the last century, but geotechnical has always been data-driven geotechnical engineering. AI is improving many parts of geotechnical engineering. Deep learning models can predict the geology encountered, say, during tunneling from TBM sensor data. Self-learning models can learn soil behavior and build constitutive models. Generative AI is amazing, can perform basic engineering tasks. It, by the way, passes the professional engineer exam. We tried it. It does pass it, okay? It gets a passing score. So successful engineers have always innovated and adopted the tools of their time. The AI revolution is no different, but it is far more transformative, in my opinion. And so, the end, we asked ChatGPT to write a Shakespeare sonnet about liquefaction. And it did a fantastic job. And with that, thank you very much, and I'll be happy to take questions if there's space for that.
It's just really an honor to have this such an amazing lecture. And it fits very well for even the vision of rock science. We are currently working on double projects on AI, and I'm sure we're going to use you a lot, Dr. Hashash. It's an honor to give Dr. Hashash the Keynote Award.
Thank you so much.
Thank you. Thank you.
Okay.
I think we will have time only for a couple questions. The first one is Reginald already reserved it. He has the mic.
Professor Hashash, that was an excellent lecture. We learned a lot and the different types of AI. My question to you is this: like even humans, you can overtrain a system. How do you make sure that all these systems that are coming up are not overtrained? Because when it's overtrained, then it's just trained to the data, its predictive capabilities actually diminish. How do you, with all what is happening, how do you make sure that you don't overtrain the system?
So that's actually the challenge that's, in fact, many of these systems, whether they only apply to us, geotech, or just the world at large. If you recall the early days of Siri or Alexa versus nowadays, it's a very different world we're dealing with, their ability to interact with us. This will not be any different. And this is where we have to potentially revisit our role as educators in the academic world or as practitioners, as we would have to develop trustworthy generative AI models versus non-trustworthy ones. Large data sets we have to deal with. Also, I mean, let's look at the reality of the technical literature. Not everything that's published is, let's put it this way, good, okay? So that is going to be the challenge with us. However, given these early results that we're looking at, that tells you the promise is there. And our role is to facilitate it, make it better, stronger, more reliable, more useful to our profession.
We have, okay. Yes, only two questions. So the first with Dr. Manoj.
Yeah, this is Manoj Varman from Rock Science, based out of India. Wonderful presentation. And the question is about the TBMs. I've been to TBMs, tunnel boring machines, many times, underground as well as in factory setups. And the sensor that you showed, some of them are for phase pressure, picking up the phase pressures in an EPB machine, earth pressure balance. And so other ones which are like sonic-based or geophysical, yes, they are being used to train the machine. And particularly, for example, for changing the cutter tools, when you change them, really, really useful, no doubt about that. But my question is about the ones which are for phase pressure and phase pressure calculation and maintaining the phase pressure in urban settings, shallow tunneling. Think about, this was EPB, for more cohesive soils. Think about slightly shield machine, which is less cohesive soils, sands and gravels, where the phase pressure drop can be enormous and very sudden. And so do you think anytime soon the AI can overtake the humans in this kind of scenario, and you can put the TBM in cruise control, adaptive cruise control, as you say?
Why not? In fact, it may be able to do a better job. You will always need to have people there so that there are alarms, things you need to pull. You can put fail-safe. But the same way we could not have thought that it might be able to go in cruise control for EPB. I suspect with the slurry machines, we might be able to. And even the machines now, we have these hybrid machines. Right, so all of that, we have massive sensors. I mean, we are actually, I'm very optimistic. And of course, for the TBM manufacturers, there's a tremendous incentive because it improves their product. Sure.
Unfortunately, for limited time, we have last question.
Yeah. Hello, I'm Fahad from University of Quebec, Chicoutimi, and I have a presentation here yesterday regarding ground response analysis, and it's my great honor having the founder of Deep Soil here. I had a lot of questions, but I will ask only one question and one request. And first question is, if we want to perform ground response analysis for specific region, as input time history, should we take only the earthquake, real or synthetic earthquake for that region, or we can take like Kobe earthquake from Japan, Kokeli from Turkish, scale to our spectral hazard and use in our analysis? What you
Let's have a conversation about it, since this is more on a, I'm not sure it would be of interest to the rest of the audience. It's a very long answer for that. You would have to use a whole large library, but
Okay.
be happy to have a conversation with you about it later.
Okay.
Sure.
And
Thank
the
you.
request, actually, I have gone through the manual from 1998. You have developed a great software. It's very easy. Every input parameters is there. So is there any way to get the 2D and 3D version of Deep Soil at future?
That would be another conversation as well.
So we'll give another applause for Dr. Hashash.